because we have another binary MESA talk. All right, so that should be up.
Yeah, we can see it, and you can go ahead.
Excellent. Okay. Before I get started, I'm just going to give everyone the takeaway. So if you remember, like, only one thing, make it this. By looking at how far CV donors lie from their expected tracks, we can infer an increasing amount of missing angular momentum loss for lower mass donors. And now we're trying to use MESA modeling to get an empirical angular momentum loss prescription as a function of period for short period CVs. So first, let's have a primer on what a CV looks like and how it evolves. A CV only really has like a handful of components. You've got the more massive white dwarf and the less massive companion star. And the companion is overfilling its Roche lobe just slightly. So matter is being ejected from its surface and falling down onto the white dwarf. Of course, that means you've got like an accretion disk, but you've also got this matter stream connecting the two stars, which is ballistic. It's just free falling under gravity. So where it meets the outer edge of the accretion disk, it's moving really quick. And it just slams into the outer rim, and you get this shock heated impact region. We call that the bright spot, and it's a pretty significant source of flux in the systems. And the balance between that mass transfer rate and the angular momentum lost from the system pretty much dictates the evolution of CVs. Angular momentum loss brings the stars closer together and causes a bit of mass transfer, but mass transfer causes the orbit to widen again. And these find an equilibrium when the donor star is just in contact with its Roche lobe. So the two are pretty closely linked. A little bit of momentum loss is balanced out by a little bit of mass transfer, but since the donor is losing mass over time, the two stars slowly move closer together as the donor mass decreases. So that balance means that CVs tend to lie on a relatively tight evolutionary sequence. Here, I'm just showing the donor tracks made by Christian Knigge, sort of like the shortish period regime, along with this vertical red line, which is the 1 sigma, sorry, that's the observed period minimum for CVs, and the band is the 1 sigma region around it. I'll get to that in a minute. For now, let's just look at this black line. The CV, the cataclysmic variable, starts off at a long period off to the right side of this plot. And as the period decreases and the donor loses mass, it comes down and left. Before it hits this horizontal section here, it's losing momentum through both magnetic braking and gravitational wave braking. So it's fairly quick up here. But then you can see the line goes horizontal, and that's where the magnetic braking probably stops being such a big deal. The donor stops losing mass so fast, and it gets a chance to contract down to its equilibrium radius. Which is smaller than when it's losing mass. So it disconnects from the Roche lobe, and that mass loss ceases, and it just stays at the same mass for a while. Eventually, gravitational waves do their thing, and the stars come closer together. The donor comes back into contact again, and your mass transfer picks back up at a period of about 2.5 hours. That used to be taken to mean that, like, at short periods, they should only be losing momentum through gravitational waves. But for various reasons, that's not really, we don't really think that's the case anymore. Then there's also this turnaround region down here, which is just caused by the donor starting to lose mass adiabatically, which means that as the star loses mass, it expands rather than shrinks. That just means that it can retreat from the white dwarf whilst keeping in contact with its Roche lobe. So rather than the stars moving closer together as the mass falls, the period starts to lengthen even as the mass is getting lower. The Knigge track is about as good a model as we have right now, but out of the box, it doesn't really line up with the observations. That turnabout period, the period minimum, is a pretty good rough guide on how well a model is doing. And you can see that the black line isn't great. I've lost my mouse. I keep losing my mouse. The evolutionary tracks can be moved to the right by cranking up the rate of angular momentum loss. The true values of that are a bit of an open question, but there are some really good ideas out there for like the potential forms that it could take. And the red track is Christian's version of this. He just beefs up gravitational losses at these short periods, multiplying them by a factor of 2.5. And you can see it does a much better job of hitting that period minimum, but it's basically just an educated guess at the physics. So just to summarize, we think there's some missing angular momentum loss at short periods, but what we actually want is to infer the angular momentum loss rates of these short period CVs. And to do that, we'll go through the proxy of mass loss rates. So there are 3 ways of measuring mass loss in these systems, but they work on different timescales. And this plot just shows you those timescales as a function of the cataclysmic variable's orbital period. We could look at the light generated directly by accretion, which is this tau obs down here, or we could look at the white dwarf temperature, since the white dwarf is heated by matter falling onto it. But you can see that these timescales are fairly short. And that means that you get a measure of the instantaneous mass loss rate, which can vary too much to be useful for what we want to do with it. What we want is like a long-term average or a secular mass loss rate. And that's going to correlate with the angular momentum loss of the cataclysmic variable. Remember, the mass loss is tied to the angular momentum loss. So one should give us the other. And the way that we're going to measure that secular mass loss rate, the long-term mass loss rate, is by looking at the radius of the donor star. If you take just any star and you strip off its outer layers, then its internal structure is going to be hotter than its mass would imply, because the pressure that was pushing down on the interior and driving fusion has been lessened, right? But the heat that was already in there hasn't escaped yet. So since the star is, for now, hotter than it would like, it inflates a little bit and expands. And that inflation relative to a star that hasn't lost mass is maintained by continuous mass loss, since the donor never gets a chance to return to equilibrium. And the result of this is that a CV donor with just a little bit of mass transfer is going to be a little bit inflated, and a CV with a lot of mass transfer is going to be more inflated. And this all takes place on the thermal timescale of the donor star, the time it takes to adjust its radius. And on here, that's this tau adj up at the top. And that's great, because this is like tens of millions to billions of years, or a billion years, I suppose. It's really like the longest timescale that we have access to. Right, so what we want to know is the mass and the radius of the donor star, since that'll trace the mass loss. And to do this, we're just going to model the eclipse light curves. I've put this up on the screen just to look pretty, but I'm not going to go into any kind of detail. It's not like a new method or anything. I can point to some great papers that outline how it works down here. But the main thing is that by modeling these eclipse light curves, we get the donor mass out of orbital mechanics, but we also get a geometric measurement of the radius. And that's important because it means we're not relying on a mass radius relationship. So we can trust what the data is telling us. All right, so we've done this for a handful of CVs. My predecessor, Martin McAllister, cranked through like 15 of these systems, and I've added another 6 over the last couple of years. So I've plotted a bunch of data on that model, that black model track from earlier. There's also these other methods, but they don't contribute that many data points. So I'm not going to go through them, but they're okay as well. And you can see that they're like generally in the right kind of area, but mostly they lie to the left, to the right of the model track. So we're just going to try and use these measurements to glean some kind of an insight into the evolution of CVs. And of course, this means comparing to the model tracks. So here I'm plotting the period excess for modeled eclipses compared to that Knigge donor track that we've seen. And when I say period excess, what I mean is if we take a donor and compare it to those evolutionary tracks, the mass period evolutionary track, how much longer is the system's period than the models suggest? Remember that the cataclysmic variable's donor is just in contact with its Roche lobe. So the period should be a rough proxy for radius. If the observed period is longer, so if that number is positive, then the model thinks that the donor radius is smaller than we observe. And that suggests some missing angular momentum loss. So this red line is the best fit to these data. And we've got the 1 sigma region shaded in around it as well. We've also got this green cross down here, which is just the extrapolated value for where the system might pop out of the period gap. And we can see that at these larger donor masses over on the right, the models are like pretty good. They're okay. There's a lot of scatter, but the error bars are quite large, so it's maybe fine. But as we get to lower donor masses, it really starts to get pretty far from zero. And that kind of suggests that we're missing more momentum loss at lower masses. And I should say that as far as I can see anyway, there's no easy way to convert this plot directly into an empirical mass loss prescription. The relationship, I think, is too complex to be done after the fact. I think it'll depend on the history of the system. So we need to run some models. And that's where MESA comes in. So I'm just going to talk for a minute. If we know the form that the angular momentum loss takes as a function of donor mass, we could eventually plug that into MESA and see how well it fits our data. I kind of argued why we can use the donor radius to measure mass loss rate, but I wasn't super specific on like the mechanics of that. But fortunately, we can use MESA and take away a lot of the legwork. If we take MESA and generate a series of models with different mass loss rates, then we'll get the radius at a given mass for a star that's being stripped of its surface at some rate, which is just like a CV donor star, right? Since we have the masses and the radii for a bunch of CV donors, we could just go to that model grid and look up what mass loss rate corresponds to each star. And then since we have the mass loss rate, we should be able to convert that to an angular momentum loss rate. If we do this for enough CVs across enough of the period space, then we should be able to construct an empirical angular momentum loss law for short period cataclysmic variables. Unfortunately, MESA is missing some physics out of the box. And that means that the radius for low mass stars is just slightly off. And I'll show some evidence for that in a minute, and I'll talk about how we fix it. But before I do, it's really worth underlining that we don't actually care too much what that physics is. We only care that the equilibrium radius of the donor star is correct. And that's because we're looking at the inflation of the star. So if the radius at 0 mass loss is not quite right, then whatever radius it gets pumped up to by mass loss is also going to be wrong. So before we make this grid, let's be sure that we're getting good quality MESA models of the donor star. We're going to use the Knigge model tracks as our gold standard that we've been looking at so far, and say if we can recreate those, then we can assume we're on about the right lines. And luckily, people have already done CV models in MESA, so we know that we have a reasonable model right out of the gate, but there are some tweaks I'd like to make. So here are 2 CV donor tracks. Same as before, top right's where it starts and bottom left is where it dies. The dashed black line is Christian's donor track with just the normal amount of gravitational braking. There's no extra fiddling going on there. It's what we want to reproduce. The solid black line up here is the output from MESA trying to model a CV. And I think it's fair to say that they don't really agree with each other. But one reason for this is a fairly easy fix, and that's the mass where magnetic braking gets shut off, or the mass where it enters the period gap, this horizontal section at the top. Christian sets his magnetic braking to turn off at 0.2 solar masses. So that's easy. We just copy that into MESA. And that gives us this blue line here, which is a lot better. We're about halfway there. There's another problem, and I've already mentioned it, and that's that the models for low mass stars are just generally too small. Really crucial that that's accurate, that equilibrium radius is accurate, since that's our foundation. So this is data from a great Stephen Parsons paper, where he's collected a bunch of masses and radii for low mass stars. I've run some just vanilla MESA models, and I've plotted how much larger the observations are than you'd expect. And you can see that the mean is about 3%-ish across the whole mass range. And to my eye, it looks pretty flat. And I should say that that's the mean weighted by the error on the data, which I've not plotted because it's just a mess. We want to push this a little bit further, though, because on top of this general model inaccuracy, Christian's tracks have an extra 4.5% inflation, just to account for the fact that stars that are filling their Roche lobes have a different structure to the isolated, spherically symmetric, one-dimensional models that MESA uses. That's not accounted for in the code, so we just need to add it in ourselves. So the question is, how do we do that? And we do it by adding in star spots. And we use this method from Summers and Pinsonneau that they wrote about in 2015. All this just boils down to adding some spots on the surface with some coverage fraction and some temperature contrast. And just to simplify that a little bit, we just use perfectly black spots and only vary the coverage fraction. Since there's some like degeneracy in the way the maths works, that's equivalent to varying both. Since the spots reduce the average surface flux, they cause the star to inflate a little bit until its surface area is just large enough to balance that reduction in flux, and that gives us what we want. So now that we have that, let's run a CV model. Oh wait, sorry, I forgot to say. We added these spots into MESA and we ran those models again. And it turns out that a coverage fraction of 40% pretty much gives us the equilibrium radius that we're after. So let's just take those and plug them into the CV models. And this is that. So now we have this new red line, and it's so good, it's actually hard to see up at the top. That's great. So, oh, and there is this little bump down here, and that's just where MESA changes what equation of state it uses for the star, but it's not a problem for us, that's fine. So now that we're confident that we have a decent CV model, let's go back and we'll generate a grid of stars with different amounts of mass loss. And we'll see if we can get some CV mass losses. All right, so this is a confusing one, but for this plot, I just ran a whole load of stellar models with different amounts of fixed mass loss and plotted their mass versus their radius as they sort of evaporate. You start up at the top here and you move left and down, and the darker colors are slower mass losses. You can see that each point is only hit by like a single model track. So all we have to do is take our CV donor's mass and radius and we look up its mass loss, and that should give us the secular mass loss rate for that CV. But there's always a caveat. I've drawn a vertical black line on here, I'm sure you've noticed. And that's the threshold where a star that's losing mass starts to worry not just about its present day mass loss rate, but it also has like a little bit of a memory. Masses to the left of that line, a star that's losing mass also cares about its mass loss history. I've got some slides on this if we want to take a look, but it takes a while to explain, and it's not that important. Most of our observations are above this threshold anyway, and it can be a bit confusing. All right, so anyway, let's take this model grid and apply it to some data and see if we can just get like some mass loss rates. We're almost up to date with the project. So from here, there's kind of like preliminary results, just as like a proof of concept. Here's a system called master OT J0014 numbers. And on the left here is that same plot again, but now there's a little red cross in the middle. And that's where the donor mass and radius for this system is. The actual distribution of that is, the actual probability distribution of that is pretty important. So I'll zoom in and you can see now that here is a black sort of line, and that's our probability distribution for the donor mass and radius for this system. All we do is we draw samples from that mass radius distribution and we look up the mass loss that it corresponds to. And that gives us this histogram over on the right there, this one. So now looking at this, we can say that this system experiences a long-term average mass loss rate of about 5 × 10⁻⁹ solar masses per year, give or take. The vertical dashed line is what a spotted fixed magnetic braking cutoff CV MESA track thinks the mass loss rate should be at this mass. And for this system, it's actually not too bad. That's just with gravitational losses, so no excess angular momentum loss. So that's about where we've got up to, but there's obviously more work to be done. The next step is to apply this to the rest of our eclipse modeled systems. Once we have a decent sample of CV mass loss rates, then we can take those and convert them to angular momentum losses. And from there, with some luck, we can construct an empirical angular momentum law for these systems. Hopefully we'll be able to plug that into MESA and get a new donor model track that should line up nicely with the data. The shape that law will take will be quite interesting, I think. It might end up looking like the Knigge optimization that we saw right at the beginning, where the excess angular momentum mirrors gravitational losses, or maybe it'll be some like flat addition. So that would become more significant as the system mass falls and gravitational waves become weaker. Or maybe it'll line up with the consequential angular momentum losses that's been floating around as an idea for a few years, where the white dwarf throwing off its outer layers every now and then contributes significantly to your angular momentum loss. Anyway, here's the summary slide from the beginning again. I hope it makes more sense than before. And if you've got some questions, I'm happy to take a stab at them.
Thank you, James. Questions? Boris has his hand up. Go ahead, Boris.
Hi, James. Thanks. This is great stuff. I have a question which is kind of a little bit outside your talk, but you have it as a boundary condition. That's the period gap. And the simple question is, do you believe in the period gap?
I think I believe in the period gap. Yeah. I see I see the evidence for it, I think, in the observations. And I mean, honestly, if I don't think do I have one with a lot of data on it? No, this is the most data I have in my talk. It's definitely less dense up in this kind of region here. And from what I understand, the systems that we do find in that region tend to be kind of weird in their own right. So,
I mean, the reason I ask this is that within the single M-dwarf community, there's the idea of something magic happening and magnetic braking suddenly stops altogether is not very well accepted. And if and what the mass of a fully convective star is also different to what we do in the CV community, and so there's a bit of a disjunct. And it could be, yeah, I don't know.
I think I sympathize with that, but my preferred understanding of the period gap that triggers it isn't that the star, because so what Boris is talking about, for people who aren't familiar, is there's a theory that when the donor star hits a certain mass, it becomes fully convective, and that shuts off its magnetic field or causes it to like drastically weaken. And that's why magnetic braking disappears. But I forget who wrote the paper now, but there's this other explanation where the magnetic field just turns itself knotty and kind of gets way worse, not necessarily weaker, but it just gets a lot worse at ejecting matter from the system. And that has basically the same effect without the convective problem. And that sounds reasonably convincing to me, but I don't understand the dark magic that is magnetism. So, you know, maybe could be.
Okay, thanks, James.
Question from Alejandra, go ahead.
Hi, thank you both for the talks. They were really instructive. I have a very basic question. I'm not really from the binary community, but you talk about magnetic braking. That is one of angular momentum laws mechanisms. And in the last 2 years, has been some papers about different prescriptions for magnetic braking, apart from the Rappaport's Kamenich formulation. And I was wondering if you consider what would be the impact of those different prescriptions on your computations. This is for both, for James and Alexei. And if the magnetic braking is actually that important that will impact your results or not.
Would you like to start, Alexei?
Well, the simple answer is that we basically, when we produce a short period system, then we basically assume the further evolutions. We don't model it from ESA. So I'm pretty sure that magnetic braking probably could be relevant to a subset of systems. And I think that's something which we definitely should at least think about better. So okay. For the progenitors, definitely not as much. I mean, the regiants are evolved and they're pretty wide orbit systems in all cases. And so then the magnetic braking is not that much.
Okay.
In my case, if the magnetic braking shutoff stuff is right, then it won't really affect what's going on down here too much, you'd think. You can see it's sort of, you can see the difference up here, if you can see my mouse again.
Yes.
So like up here where magnetic braking's still on, it could have an effect, but that's not really, I don't focus very much on the long period stuff. So maybe not.
It won't be important for your for what you're looking for.
For what I'm looking for, where I'm looking, all of the magnetic braking is not considered much anyway. But one theory for that excess angular momentum loss is that magnetic braking doesn't shut all the way off; it just gets way weaker, and maybe the different prescription would have an effect.
I'll give you that. Okay, thank you both.
Okay, I don't see any more questions. So thanks again, James. And
how do I stop? There we go. Okay.
and I'll stop recording.